Hey everyone, and welcome. Have you ever looked at a box and wondered how we get from a simple flat piece of cardboard to a solid 3D object? Well, today we're jumping right into the geometry of 3D shapes to figure out exactly how they're built, how we measure them, and, why any of it actually matters. Let's get started. Believe it or not, everything solid, from the phone you're holding to the building you're in, it all starts with simple, flat, two-dimensional shapes. Seriously, think about it. Squares, triangles, circles, they are literally the Lego bricks of our physical world. But that's where the magic happens, right? What happens when we take one of those flat shapes, say a rectangle, and we kind of stretch it out, give it some height? Well, all of a sudden, it has depth. It can hold stuff. It's got volume. So in this first section, that's exactly what we're going to explore, how these simple flat shapes morph into solid objects. And we're going to be talking about a really special group of shapes called prisms. Okay, so what in the world is a right prism? Let's break this down. First, you've got two bases that are exactly the same, and they're parallel to each other. You can think of them like the floor and the ceiling. Then you've got the walls connecting them, and those walls are always rectangles. Now here's the key part that makes it a right prism. Those rectangular walls have to stand up perfectly straight at a 90-degree angle to the base. No leaning allowed. All right, so imagine you need to measure the entire surface of one of these 3D things. I mean, how do you even do that? You can't just slap a ruler on it and get the whole picture at once. It's got all these different sides. Well, luckily for us, some clever folks came up with a pretty brilliant solution. And that brilliant idea is to basically do the exact opposite of what we just did. Instead of building the shape up, we're going to carefully unfold it and lay it out completely flat. By doing this, we turn a kind of tricky 3D problem into a bunch of simple 2D problems we already know how to solve. And this is exactly what that looks like. This awesome flat pattern is called a net. See that? You've got the two triangular bases, kind of like wings on the side, and then the three rectangular faces that used to be the walls, all laid out in one piece. It's such a great way to see how a 3D shape is really just a collection of 2D shapes folded together. This is literally how things like cardboard boxes are designed and made. So yeah, to give it its official name, this flat pattern is called a net. Just think of it like the Prism's blueprint. It's the absolute key to letting us measure every single surface all at once. So why is this net concept so darn useful? Well, it brings us to what I like to call the wrapping paper problem. Imagine you've got a gift to wrap. How much wrapping paper do you actually need? That's not a trick question. That's a surface area question. You need just enough paper to cover every single face perfectly. And using that net makes this super, super simple. It's really just a three-step process. First, you find the area of your two bases, the top and bottom. Easy enough. Next, find the area of all those side faces. And in geometry, this has a fancy name. We call it the lateral area. Then for the final step, you just add it all up. And that's it. That's your total surface area. And of course, for all you pros out there, there's a nice clean formula that sums this whole process up. Surface area, or SA, equals the lateral area, LA, plus 2 times the base area, B. Now, this isn't some new, scary math. It's just a really efficient way to write down exactly what we just did. It's a great shortcut to make sure you've counted the sides, the top and the bottom. Okay, so we've totally mastered the outside of the shape. But what about the inside? This brings us to a whole different kind of problem. Instead of wrapping a box, let's say we're trying to fill a fish tank. The question now is, how much water can we actually fit inside this thing? Now, you might be thinking, okay, so I'm going to need a different rule for a triangular prism, a square one, a hexagonal one. But here's what's so powerful and just so cool about this. The core idea is always the same, no matter what shape the base is. And here it is, that beautiful universal formula, volume equals base area times height. That capital B is the secret sauce. It just stands for whatever the area of the flat base is. Once you calculate that, you just multiply it by the height, h. It's like you're figuring out the area of one super thin layer at the bottom, and then just stacking identical layers all the way to the top. It's an incredibly simple idea that just works every single time. Okay, so now it's time to put these two big ideas, surface area and volume, head to head. Let's get practical. Imagine we're designing an aquarium. We've got to think about two things, right? How much water it can hold for the fish, and how much glass we need to actually build it. So let's be absolutely crystal clear on the difference. Surface area is the wrap. It's about covering the outside, and we measure it in square units, like square inches. Volume, on the other hand, is the fill. It's about the capacity on the inside, and we measure that in cubic units, like cubic inches. They're two totally different things, but as you're about to see, how they relate to each other can be, well, pretty surprising. And this right here is where things get really fascinating. Just take a look at the numbers for these two tank designs. The rectangular tank, it clearly holds more water, right? It's got a bigger volume. But now, look at the surface area. The trapezoidal tank, the one that holds less water, actually needs more glass to build. Isn't that wild? It's a perfect example of how the relationship between how much something holds and the material needed to make it isn't always what you'd expect. Which brings us to our final big thought here. This isn't just about a math class problem. This is about smart design and real-world efficiency. Think about it. Creating the most space with the least amount of material. The answer is literally all around us, from the way nature designs things to how engineers build everything from soda cans to shipping containers. It's a core principle of efficient design. Something to think about. Thanks for tuning into this explainer.